Greetings, Panthers. Dr. Augustine again. Today we are going to take a look at partial pressures and mixtures of gases. The video will cover chapter 6.6 intro, and we are going to take up the question of what happens when you have a mixture of gases. So if you remember, the ideal gas equation was used for pure gases, or you may not have realized that, but the ideal gas equation is appropriate if you have a pure gas. So if you have just oxygen or just nitrogen or just fluorine gas or something like that. But I'm going to show you how you can use the ideal gas equation to be used for a mixture of gases. And then we will introduce what's called Dalton's law of partial pressures for gas mixtures. And I will show you a specific case of where this is useful in collecting gases over water, and why, if we collect gas over water, it's an example of partial pressures. That may not be obvious. And in that, we will introduce the concept of vapor pressure. So let's begin with PV equals nRT. This is our standard equation. This is the ideal gas equation. And let's pretend we have a mixture of gases. So suppose we have a container, and in this container we have gas A and gas B in some ratio. Doesn't actually matter what the ratio is. We could have a lot more B than A. We have some amount of A and some amount of B. Well, on the container that we probably have a pressure gauge which allows us to measure what the pressure is. But what that's actually measuring is the total pressure in the system. Okay, so the pressure gauge, in other words, can't distinguish between A and B gases. All it's measuring is the total pressure. So if we think about the measurement we're going to actually make, we're going to have some pressure gauge and we're going to measure a total pressure. That's going to be a contribution of all the different gases. So we can actually rewrite this as P total V equals N total RT. Okay, temperature is going to be the same. Doesn't matter whatever that temperature happens to be. The volume's the same. R is the same. But the pressure actually results from all the different gas molecules. All those A's and B's in there add together to have some total number of moles. Okay, so it's the same ideal gas equation, except now we have N total instead of whatever the individual gas is. That's the first piece of understanding. The second piece of understanding then is that P total is actually equal to the sum of the pressures contributed by each individual gas. In this case, we have two gases, A and B. But if we added a third gas, a C, then we would have to add a third contribution due to gas C. And this could go all the way out to infinity, no matter how many gases we have in our mixture. Okay, we'll just do two because that's kind of the simplest way to look at it, but you can imagine any number of gases would give us the same result. Okay, so this equation right here just simply says that the total pressure is equal to the sum of all the individual partial pressures. These are called partial pressures. And what we measure on the pressure gauge is just adding the contributions up from all of them. This is called Dalton's law of partial pressures. Okay, so a good question is, what are these individual partial pressures? Well, we can write each individual partial pressure just as PV equals nRT, except now the number of moles is whatever that individual gas is. So PAV equals NART, PBV equals NBRT, PCV equals NCRT, etc. If we had more gases, we would keep adding these up, we would keep adding these together. So my P total equation is really equal to NART over V plus NB RT over V plus NC RT over V. In other words, each individual gas, we could rearrange this equation and solve for the partial pressure, and then we could plug that partial pressure back into this Dalton's law of partial pressures. We end up getting an equation that looks sort of like this. Again, if we had more gases, we would have more terms. Now, if you look at this equation carefully, you notice RT over V is common for every single one of these equations. So we could rewrite this P total equals N sub A plus n sub b plus n sub c times RT over V. We can pull out those common factors. And also, if you recognize, Na plus Nb plus Nc, that's equal to N total. That's the total number of moles of gas. So Na plus Nb plus Nc is equal to N total. And then we get back this equation, right? P total is equal to, P total times V is equal to N total, which is the sum of all these individual pressures, times RT. Okay? So if we have the total pressure and we have T and V, we can figure out what the total pressure is. And if we have some of these number of moles, we can figure out one of the individual ones. All right, that doesn't turn out to be a super useful way to do this. So the other thing we might be interested in is, what about if we want to find out what this individual partial pressure is? That might be a more interesting thing to do. So what we can do in that case, we can set up a ratio. We can set up a ratio of the pressure due to A divided by the total pressure. And that's going to be equal to Na RT over V divided by N total RT over V. All I've done is I've rearranged this equation, and I've rearranged this equation, and I've set up a ratio between the partial pressure of gas A divided by the total pressure. That is equal to the A term, RT over V, and the total term, RT over V. And obviously, if you look at that equation, you notice RT over V is common to both of these. So I can pull those out of the equation. So I have something like this. Na divided by N total times RT over V is equal to this ratio. So this introduces a new term, and the new term is this Na over N total. We call this the mole fraction, X sub A. So X sub A is the fraction due to the contribution due to A. And we could write this for each individual gas. Gas B would be N sub B over N total. Gas C would be N sub C over N total. And remember, N total is number of moles of A plus number of moles of B plus number of moles of C equals N total. So let's rewrite that in a little bit cleaner fashion then. PA over P total is equal to the mole fraction of A. And actually, probably more useful, the pressure due to gas A is equal to the mole fraction of A times the total pressure. Why is that more useful? Well, if you remember back in my original drawing, we have the total pressure. That's usually pretty easy to get. That can be measured with a pressure gauge. So we know the total pressure. If we can figure out what that mole fraction is, then we're going to be able to find out what the partial pressure due to that, whatever that particular gas is. Okay? So we have two different ways of finding the partial pressure. The first way is an equation that looks like this. So if we have temperature, if we have volume, and if we know the number of moles, we can find the partial pressure. Or if we know the mole fraction, mole ratio, we can also, and we have the total pressure from the gas gauge, we can also find the partial pressure. So quite a few problems actually end up involving either this equation or this equation, and a lot of them you actually could use either one to solve. I'll show you an example in a minute. Okay, so these are key equations for solving this problem. Now, when would we use this experimentally? And that's where this picture comes into play. So oftentimes, one way to collect a gas in a chemical reaction is to have some sort of setup where you have a chemical reaction, you have a sealed stopper, you have a glass tube, which brings the gas into something like a beaker or something that has water in it. And as the reaction generates gas, the pressure builds up inside of the beaker, forces water out of the beaker, and you can begin collecting that gas in here. The reaction that's being shown here is one that's actually a pretty common reaction. And if you're at HPU, you actually did this experiment. It's a displacement reaction between hydrochloric acid and zinc metal to form zinc chloride plus H2 gas. And this isn't quite balanced, so I need to put a 2 out in front here. Okay, so here's our chemical reaction. We have a piece of zinc, we have hydrochloric acid reacting with it, and hydrogen gas is one of the products that gets formed. So that's being depicted here in this. So as the hydrogen gas gets generated, it's being pushed out of the tube here, pushed through this tube into the beaker, and the pressure builds up and it starts forcing the water out of this container. Now you might be asking yourself, well, why is this a partial pressure experiment? Because why is this dealing with a mixture of gas? This only generates hydrogen. That's the only gas that's being formed. Well, here's what's going on the molecular scale. So let's take a look at one of these bubbles. Let's say this is one bubble. Let's say here's another bubble. And inside of the bubble is hydrogen gas. And obviously there would be lots of hydrogen gas molecules inside of this bubble. At the very interface of the gas bubble with the liquid water, we have water molecules. And the gas inside of the bubbles are in motion. That's one of the principles of the kinetic molecular theory, which we'll talk about in a little later. But these gas molecules are always in motion, but the water molecules are also in motion. So they have some energy associated with them because the water molecules are actually moving around. They're not stationary. They're in a dynamic state. And as this bubble moves its way through the water, some of the water molecules have enough kinetic energy that they can break free of the surface tension and get converted into gas phase water. Not a lot, but some of them do. Some of them will actually return, and when they hit the walls, they'll stick back to the water, but while some are returning, some are going into the gas phase. This is called equilibrium. And this phenomena that we'd be observing is actually known as the vapor pressure of water. And the vapor pressure scales with temperature. So the hotter this experiment is, the warmer the reaction mixture is, the more water is going to get picked up into these gas bubbles. The reason why the more water gets picked up in the gas bubbles is because these water molecules have more kinetic energy and more of them are able to break free and go into the gas phase. Now it turns out water vapor pressure has been very well studied, so we can actually look up in a table. If we know the temperature, we can find the vapor pressure of water at that temperature. And at different temperatures, the vapor pressure changes. Okay, and of course, you'd want to know the vapor pressure in whatever pressure units you're using to measure your overall pressure. But the bottom line is, as you bubble these gas molecules through the liquid water, you're going to be picking up gas phase water. So then your reaction is no longer just going to be hydrogen. It's going to be hydrogen plus H2O. And that means the pressure that you were to measure is actually equal to the pressure due to hydrogen plus the pressure due to water. And now it becomes a partial pressure experiment. So we would need to know this pressure, this vapor pressure of water. If we knew the temperature, we could look up the vapor pressure of water, or the problem might have it in it. The total pressure would usually be given to us because that's something that's easy to measure, and then that would allow us to calculate what the partial pressure is due to hydrogen. All right, so our next video, we're going to go over a specific problem looking at this exact type of problem.